Welcome back. In this segment, we're going to explain why the master theorem works. Instead of giving a formal proof, we're just going to provide the intuition behind the proof. Now remember how we trace the execution of a divide and conquer algorithm like the merge sort algorithm. We represented the sequence of recursive calls using a tree like this one, where the root node of the tree is the initial call to the algorithm, and then the two children node of the root node correspond to the two recursive calls that are made at the top level. And then every node corresponds to the execution of the merge sort procedure, which contains two recursive calls, all the way down to the leaf nodes of the tree, which represent the base case execution of the merge sort algorithm. Now, this is what we call a recursion tree, since it traces the recursive execution of the algorithm. The first thing to realize is we don't really need to indicate the contents of the node, because every time you call this algorithm with an input of this size, that is 10, you will get a tree with exactly the same shape. The actual contents of the input sequence does not change the sequence of recursive calls. So from now on, we're going to represent these recursion trees as follows, with a dot for each execution of the main body of the algorithm and edges representing recursive calls, all the way down to the base case executions of the algorithm. Now remember that in the case of merge sort, the value of b is equal to 2, which means that the input size n is cut in half every time for each recursive call. Now because this number here is even, at the next level down we have two sequences of the same length, namely 5. Unfortunately, at the next level down, because 5 is not an even number, we have two sequences of length 3 and 2 which are not equal, which is why we have an unbalanced tree here with leaves at different depth in the tree. So to avoid this asymmetry in the tree, we're going to assume that the initial length of the input sequence is a power of b. What this means is every time we divide by b at each level, we're going to guarantee then that we have sequences of equal length. And in particular, what it means is that all the leaf nodes are going to be at the same level down at the bottom. And furthermore, we're going to assume that the base case of the recursion assumes when n is equal to 1. So here is what a tree is going to look like with all the leaf nodes at the same level, because n is a power of b to the k in general. Now, if I give you this particular recursion tree, and I ask you what are the values of a and b in this particular case, how do you use the tree to determine those values? Remember that in a divide and conquer algorithm, the value of a is the number of subproblems, that is the number of recursive calls that the algorithm makes. So we can tell here, since every node that's not a leaf node has two children in the tree, that the value of a is equal to 2. However, it's impossible to tell the value of b just by looking at the tree. All we know is that at this level, the input size is equal to n, and that at the next level down, the input size is equal to n over b, and then the input size is equal to n over b squared, all the way down to input size being equal to 1 at the leaf node, according to this assumption. But that's not enough to determine the value of b. For example, notice here that the fact that b and a are both equal to 2 is a coincidence. A is equal to 2 because every node has two children, and b is equal to 2 because the input sequence is cut in half. But it is quite possible, and we've seen examples of that, where the value of B is different from the value of A. So we can't tell the value of B just by looking at the tree. So let's perform some simple computations here to think about this a little bit more. The first thing is to define the concept of a level. So think of a horizontal line going through this node, and we're going to call this level 0. And then draw a horizontal line across these two nodes, and that's what we call level 1. And so on and so forth for these nodes at the next level down, level 2, and the leaf nodes in this case appear at level 3. First, we're going to find a formula for the number of nodes at each level. So at level 0, we find a single node. At level 1, we have 2 nodes. At level 2, we have 4 nodes. And at the leaf level, number 3, we have 8 nodes. Now, notice how the number of nodes doubles every time we go down to the next level. That's not a coincidence. That's because A is equal to 2. In particular, notice the number of nodes on the level 1 is equal to A because there's one node at the root, and the root has exactly A children, or makes A recursive calls. So the root, or the level 0, will always have one node. The next level will always have A nodes. And of course, the next level is going to have 8 times more nodes than the previous one, because for every node at that level, you add A nodes in the next level. So at level 2, the number of nodes is going to be equal to A squared. At level 3, the number of nodes is going to be equal to A cubed. Now, we can generalize this column by noticing that A is equal to A power 1, and 1 is equal to A power 0. In other words, the number of nodes per level is always equal to A to the power, the number of the level. The next step is to compute the size of each node, or more precisely, the size of the input at each node. So according to our assumption here, the size of the input for the leaf node at this level is 1. Now, what is the input size at the next level up? Well, remember, the input is cut by a factor of B to go from here to here. So it must be the case that if we start from some number, you divide by B, you get to 1. You must have started with an input size of B at this level. And similarly, if you started from some number, you divide by B, and you end up being at size B, you must have started with the size B squared at this level, and so on and so forth. And so the conclusion here is that the input size at the first call to the algorithm must be B cubed. Well, that's not a surprise. That's what we call the value of n. N is a power of B, and in particular, k must be equal to 3 in this case. Now, what is k? Well, k is the power of B that's equal to n. Another way to say that mathematically is that k is the log base B of n. And so the interesting thing here is, notice how the number of levels below the root node, so not counting this level, is 1, 2, 3. It's not a coincidence that this number 3 is equal to the value of k. In other words, the log base B of n. Because starting from B power k, how many times does it take until you reach 1 if every time you divide by B, the answer is, by definition of the log base B of n. So the conclusion here of this analysis is that if the input size is B to the k, then the number of levels in the recursion tree below the root node is exactly equal to k, where k is the logarithm base B of n. Now remember, we started this discussion by asking what the value of B is. And again, we cannot determine this just by looking at the recursion tree. However, we know that n is equal to B cubed. So if we know the value of n, then we can determine the value of B. Let's say I know that the size of the input to the original call was equal to 27. then I can infer that 27 is equal to b cubed, and therefore b must be equal to 3, since 3 cubed is 27. So in conclusion, what we learn from this analysis of the recursion trees is that 1. We can determine the value of A just by looking at the number of children of each node that is not a leaf node. 2. We can determine the value of K, that is the number of levels below the root node, just by counting them. And finally, using K, if we know the value of N, namely the input size at the root node, then and only then can we determine the value of B for this algorithm.